Hey everyone, my name is Skylar McGaughey. I'm going to be a sophomore this year at UNC and I'm a chemistry major. I'm from Raleigh, North Carolina, and I really want to be a peer mentor this year because I mastered both Chem 101 and Chem 102, and I would love to help kids not only understand general chemistry more, but also appreciate and enjoy chemistry as much as I do. So let's get started. Okay, so this is the problem we're going to be working today. I chose this problem because it's from Unit 3 in Chem 101, which I think is just a more difficult unit in general. And it combines multiple different concepts throughout the semester, and I love this problem because it has both a mathematical and a concept component, and both the math and the concepts are important to master to be successful in Chem 101. So let's get started. Astronomers have detected hydrogen atoms in interstellar space in the n equals 32 state, an excited state. Suppose an atom in this excited state underwent a transition to the n equals 30 state. What is the wavelength in meters of light associated with this transition? So first, for someone who didn't necessarily know how to start this problem, I would say begin with an equation that uses the variable you're looking for, which in this case is wavelength or lambda. So based on our equation sheet, we know that lambda is equal to Planck's constant times the speed of light divided by the change in energy. Both of these values are on the equation sheet and use 4 significant figures. So the only variable we need to find is the change in energy. We can find this using the Rydberg equation, which is the change in energy is equal to negative Planck's constant times the speed of light times the Rydberg constant multiplied by 1 over the final state squared minus 1 over the initial state of the atom squared. When we plug in these 3 variables we know, it will come out to negative 2.179 times 10 to the negative 18th joules, the units are very important, multiplied by 1 over 30 squared minus 1 over 32 squared. Remember, it's final minus initial. When we plug this into our calculator, it will come out to negative 2.932 times 10 to the negative 32 joules. We're not done yet. So we take this energy value, delta E, and we plug it back into this equation. The result, when we plug it into our calculator, is that we get an answer of lambda is equal to 6.775 times 10 to the negative 4 meters. Remember, we use 4 significant figures because all of our constants have 4 significant figures. And if you need to go back through and check, you will see that all the units cancel out and leave you with only meters. So you know that you're probably right. So based on what we've looked at so far, in part B, is this light absorbed, emitted, or is it impossible to know? This is definitely more of a concept question. So the first thing that I would recommend to look at is what was given in the problem above. The change in energy states is from an excited state in n equals 32 to a less excited state in n equals 30. When we move from a more excited state to a less excited state, light is usually emitted. This is the correct answer, and it can also be confirmed mathematically because the change in energy is negative, meaning that it was going from a higher energy level to a lower energy level. So that's all you need to know, and it's actually not that bad. So thank you.